Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is magnetic fields and forces, and this is actually a video that the grade 11s and the grade 12s can use. Grade 11s, you're going to be learning about this topic for the first time in this amount of detail, and grade 12s, you need a review of these ideas from last year for what we are going to do on our next video. So this is a video for both of you guys. So what I've done is I've taken the unit schedule and the learning goals and success criteria for the grade 11s and put them on this page, and I'm going to ask the grade 11s to pause the video and have a look at them, and then the grade 12s, you can move on. You can let me move on a few seconds in the video to the next page. So grade 11s, pause it now and then come back. Okay, and grade 12s, here we go. This one's for you at the top of the page here. Here's where we are in the unit schedule and with the learning goals and success criteria. And so some of the questions that we're going to address today are questions about what magnetic fields are, what they have to do with magnetic forces, and then we're going to look at some applications of these magnetic fields. Anyway, to get us started, let's do a quick review of probably the most important thing you got to remember with magnets. That is the law of magnetic poles. Just like we have the law of electric charges, which says that like charges repel and opposites attract, same goes for magnets, only now we're not talking about positives and negatives, we're talking about the north pole and the south pole of a magnet. So as you can see in the first diagram here, you see two north poles of bar magnets repelling, or two south poles repelling, and we can write that down just like this. We can say likes repel, and of course right here we can say that opposites attract. Now, there are some other things you should know about magnetic poles that are a little bit different than electric charges, and one of the most obvious is that you never have just a single magnetic pole. In other words, there's no magnetic monopoles. There are only magnetic dipoles, which means you can only have a north along with a south. Like if you take a bar magnet, for example, and I'm sure all of you have played with these at some point in your life. Looks kind of like this, a north end and a south end. And if you were to break that in half, you wouldn't end up with just a north and just a south. That's actually never been observed to happen. You would just end up instead with a smaller magnet that looked like this and a smaller magnet that looked like this. So there's no magnetic monopoles. In fact, if you do observe a magnetic monopole, I remember a professor once telling me, make your way to the Nobel Prize Committee because you're going to win a Nobel Prize. So I'm guessing that we're probably not going to see these anytime soon, although who knows, maybe physics has progressed to the point or will progress to the point that we do have them. Anyway, moving along, let's see how we can now use this idea to predict what happens when we are in the presence of a magnet. So first off, what do we mean by magnetic fields? Well, the grade 12s have been studying something called electric fields and gravitational fields, and so have the grade 11s, although the grade 12s we've talked about these in a lot more detail in terms of the equations. Grade 11s, you guys are just getting used to them. However, what we mean when we say the word field is we mean a region around some object where force can be exerted. In the case of the Earth, there are two important fields. The one that you're familiar with on a daily basis, of course, is gravity. The gravitational field of the Earth attracts all masses down toward the center. However, there's another one that is in many ways equally important, and that is what's called the magnetic field. So let me get you started with a diagram here. By the way, these diagrams are off of Google image searches for the most part. Some of them are from the grade 11 physics textbook, Physics 11 by Addison Wesley, and still others are from the grade 12 book, Physics 12 by Nelson. Anyhow, what is this? This is a picture of a rock. You can see the rock right here. And these, what look like pieces of metal here, are actually small nails, which you can see are stuck to the rock. Now, nails are made of iron, usually. And you may know that things that are iron, or made of iron, can be picked up by a magnet. Well, this is actually a natural magnet. It's given the name a lodestone, and since ancient times, people have known about these magnets, these natural magnets called lodestones. They're actually minerals which are oxides of iron. So if you take iron and you combine it with oxygen, which is essentially what happens when things rust, but also in certain combinations, I believe it's Fe3O4. I could be wrong. The chemists are probably getting all upset with me. Check that out. When it combines like this, you can have some magnetic properties in the rock. And since ancient times, people have realized that these stones, of course, can attract iron, like you see here. Another interesting property they have is that if you take a really, really tiny piece and you balance it on a peg, let's say, so that it can kind of swivel around, it always lines up in a roughly north to south direction anywhere on Earth. And so this gives us the idea of navigation, and of course it's the basis of a compass. So imagine Mother Nature has given us a compass from which we can navigate. How would life be different if we didn't have this and navigation was so much harder, especially out at sea where there's no landmarks to guide you? So what is it that's causing the lodestone to act as a compass? Well, now we look at Earth's magnetic field. Maybe you've seen diagrams that look like this. It's well known that Earth itself actually behaves like a gigantic magnet. We're not exactly sure why that's the case. We believe it has something to do with the molten core of the Earth and possible swirling currents of molten rock which have charged particles in them. Their motion might just provide the magnetic field that we're going to investigate later on in this chapter, because as you're going to see, moving electric charges can produce magnetic fields. But in any case, if you step back from Earth, which means to look back from a satellite or maybe one of the lucky few astronauts that went to the moon, if they could look back on Earth and if they could see these magnetic field lines, they would look something like this, of course in 3 dimensions. So they'd be coming all around the planet like this in a sort of donut or bagel shape. And the Earth's magnetic field, of course, is what the lodestone lines up with when you use it as a compass, and that, of course, directs us either to the north or to the south, and from that we can figure out east and west. Now, this, of course, up here is the north geographic pole. This is the axis on which Earth spins, and if you go right up to that point and look straight up, you will see at night the North Star, the pole star, Polaris. And a few degrees off from that is actually where the magnets or the compasses would be pointing. So we call that the magnetic North Pole. You can see that magnetic north and geographic north are not the same, and as it turns out, the Earth's magnetic field is gradually changing over time. We have evidence that it's been different in the past, and we know it's changing today, so we believe it will continue to change into the future. So this can make navigation a little bit difficult. You've got to update your maps every now and then, and you have to be careful if you're navigating by compass. However, just so you know, what this white and red pointer is showing is the direction that a compass needle would point. And we will, if you do some reading in your book, this is mainly for the grade 11s, you will learn, maybe surprisingly, that even though they call this the North Magnetic Pole, it actually behaves like the South Pole of a magnet, and the South Magnetic Pole behaves like the North Pole of a magnet. I'll explain. In this next diagram, you see a bar magnet. The South and North Pole are shown, and then there's these strange lines around it. Maybe you did this when you were younger and playing around with magnets, I don't know, grade 4, 5, or 6. What you do is you take a magnet and you sprinkle a bunch of pieces of iron, called iron filings, all around the magnet, and they always form this shape, which looks a lot like the Earth's magnetic field. You'll notice that the iron filings bunch up near the poles, indicating the strength of the magnetic field there, and then they spread around in a loop here like this. Unlike the diagram here, where you can see arrows here, these arrows are a human invention where we have arbitrarily said, okay, let's assume the direction goes one way, but you don't see that in nature. So let me explain to you what we're going to do here. We call these lines the lines of force, if you will. And these lines of force show us the direction that any natural magnet will experience. It'll experience a force in that direction. However, we have to assign it a direction. So what we do is we give it the direction from north to south. Now, we could have done it the other way if we wanted, but I guess this is just how scientists agreed to do it. So if you ever see me drawing the lines of force around a magnet, it'll be from north to south. And so the way I remember this is I like to think that everyone wants to go south for the winter. Think of that and you'll always know the direction of the magnetic field lines, out the north end and then into the south end like this. Now if you take a compass, as you see in this last diagram here, in this row, the compass needle points in the direction that is south. And in a compass needle, the pointy end is supposed to be telling us what direction is north. So that's like a little north, and that's like a little south. This is like a little north, that's a little south, and so on. Now, if we go back to Earth here, that means that since up is north on most maps of the Earth, therefore, a compass needle pointing north is really directing us toward the south end of a bar magnet. And therefore, even though this is called magnetic north rather, even though this is called magnetic north, it's actually behaving like a south end of a magnet. And that's why these diagrams I lined up with south at the top. All right, this is further explained in your textbook in case you're wondering why south is at the top. So there you go. Now you know what magnetic field lines are, and you know what direction they point, and you know the relationship to Earth. So let's look at some more complicated scenarios. For example, here you see the ends of two magnets, and the iron filings have been sprinkled around. What do you notice about these? They are sort of coming toward one another and then repelling. Maybe I'll do better with a color there. See them repelling like that. Why do you think they're repelling one another? Why can't they join up? After all, they do join in this next picture here. Here they come around rather nicely. The grade 12s will recognize that this looks a lot like the electric field due to point charges. These would be like charges and these would be opposite charges, but the grade 11s we haven't studied that yet. However, for you grade 12s, there is a parallel with magnetism. Grade 11s, can you figure out what it is? These are two like poles. They could be norths or they could be souths. It's impossible to tell just by looking at the diagram. It'll put south with south, north with north. And of course, if this is a south here, then this would be a north. There's a traction happening here. Or if this was a north, this would be a south. All right? Suppose we take a bar magnet and we bend it into a horseshoe shape. Then you have what's called a horseshoe magnet. And again, you can see, since one of these ends might be north and the other might be south, or would be south in that case, the lines come toward one another in between, and you see them looping around here. And then they go all the way around the outside, as you would expect, based on a single bar magnet. All right, so there's many other shapes that you can make. You could introduce a third magnet or four magnets. There are magnets that are in the shape of a disc. Lots of different possibilities. You can arrange them however you want, and you can make ever more complex magnetic fields. All right, let's move on. So now what we're going to start to do is look at the link between electricity and magnetism. It's a really neat observation that if you take a wire, as you see in this diagram here, and you pass a current through it, so suppose the, I don't know, let's say that the negative end of a battery is connected here, and of course this would go down here. This would be the positive end of the battery. For example, if you connected this like so, there's a negative terminal, positive, negative, positive, negative, positive, etc. If you did that, and then you sprinkled iron filings around, let's say, a sheet of paper that this wire was poking through, look what the iron filings do. This time they go around in a circle like this. We now have two interesting observations. One, that a current carrying wire, in this case the current would be going from positive, remember out the positive terminal we've learned, and up to the negative terminal. So in this case, not only does an electric current produce a magnetic field, but it has a definite shape. This diagram here shows you how to figure it out. This is a diagram of someone's right hand, and what he's done is he's pointed his thumb in the direction of the current. So the first thing to realize is that if you take your right hand and you make the thumb in the current direction, then the fingers will go in the direction of the magnetic field. Now the magnetic field is given the letter B, and it actually is a vector because it has direction. Why is it the letter B? I have to admit I don't know where B comes from. I guess they can't use M because that might get confused with mass or maybe mega or something. So B it is. The fingers are in the direction of the magnetic field. The thumb is in the direction of current. And we call this the right hand rule. Now there's going to be several right hand rules. So this is right hand rule number 1. I also like to call it RHR number 1 for short. And it tells you the magnetic field due to a single current carrying wire. There are going to be more, so this is just number 1 of actually 3. Here's a diagram here from your textbook which shows another way of looking at it so that if you're not very good at drawing three-dimensional pictures like this, everyone will be able to do this. Try this. Imagine a wire where the current is kind of going into the computer. This is supposed to be drawn in perspective. The current's going into the computer. The way we show that a current is going away from us in a third dimension is we draw this X over here. So if you're ever dealing with vectors and directions and you see an X with a circle on it, it means that something is going away from you. The way to think about this is if someone were to shoot an arrow at you, think of a bow and arrow, all right? So bow and arrow, here's the arrow with the feathers at the back here, and here's the tip of the arrow. If someone shot an arrow right at you, what would you see coming to you first? You'd see the tip of the arrow, which would look like a little dot coming toward you. But after the arrow passed you, you would see its feathers, and the feathers usually form a little crisscross like that. So that's why mathematicians and scientists use X with a circle around it to show you something that is moving away from you. That's what this means, away. So this is showing you a current going into the computer screen. So we draw it as an X there, or over here you see it a little bit better. Current flow into the page. Now, take your right hand, put your thumb in the direction of current, so your thumb should actually be sort of poking into your computer screen right now, and look at your right hand fingers and curl them like this guy's doing. You'll notice that they are curling in this direction, and so this is a way to use the right hand rule if the wire is going away from you. Alternatively, if the wire is coming toward you so that the current is coming out of the computer screen right toward your face, now we think of an arrow that's flying right toward your face. What would you see? You'd see the tip of the arrow, that's a dot. So in this situation, scientists and mathematicians draw a dot with a circle around it. And that's what you see here. A dot with a circle around it. And so take your right hand, have your thumb pointed directly at your nose, or your eye, let's say. Take your right hand fingers and curl them around, and you'll see they're going this way. Sorry, what have I done here? I've made a mistake back here. This I drew the wrong way. I hope some of you were paying attention and thinking, what is this guy talking about? The direction there is this way. So just to go back, the reason why I goofed on this was I'm using my right hand to draw, not to write. Sorry, not to do the right hand rule. So going back here, thumb pointing into the computer screen, right hand fingers wrapping this way, which, let's use the correct words here. This would be clockwise, or CW, as I sometimes write it. Okay? Here is where we would have the thumb coming toward us, the fingers wrapping this direction. This will be counterclockwise. There we go. Counterclockwise, or CCW. Okay? So that's right hand rule number 1. Gives you the magnetic field due to a current carrying wire, and now we know how to draw it if the wire is going straight up and down the computer screen or into and out of the computer screen. Okay, moving on. Suppose you took the current carrying wire, as you see in diagram A here, and you started to bend the wire like you see in diagram B, and you bent it all the way around so that it went in a loop like you see in diagram C. What would start to happen? Well, if you took this loop, which you are currently looking at in a cross-sectional view, and you started turning the loop so that now it was kind of edge on. See if you may need to pause the video to make sense of this diagram. It took me a while the first time I saw it. Pause the video and see if you can imagine this happening in 3D. It might help you to take a wire, like, or maybe the cord of your earphones for your smartphone, or just a wire that's attached to an appliance, and bend it like this. Use the right-hand rule number 1 to predict each of these magnetic fields, symbol B vector. And as you start curving that wire into a loop shape, look at what's going to happen. As you do that and then rotate the wire so it's edge on, you'll start to see that the magnetic field on top, you can see here, the current is going away from you, so that's an X. That's going to give you a clockwise magnetic field. But down here, where the current is coming out at you, so that's a dot, you will now have counterclockwise. And what do you notice? What's really neat about this current loop is that on the inside, you see the magnetic field due to the lower portion of wire going to the left, and the magnetic field from the upper portion is going to the left. So these guys add up. And if you had a whole bunch of loops, like if you coiled this loop many, many times, coil a cord around your finger, you'll see what I mean. We call that a helix, by the way. Then you might get something like this. Here's a diagram. This one's out of the grade 12 book. And you can see they've connected a coil of wires, a helix, to a power supply. And they've sprinkled some of those iron filings. And here's what you get. You get a magnetic field, which you can see from the iron filings. I'll do this in yellow so it's a bit easier. Goes right up the middle like that. You get a nice uniform magnetic field. And then it loops around like this. You ever seen this before? Of course you have. It looks kind of like this down here. The magnetic field due to a bar magnet. Here's how to figure it out. First of all, we take our right hand once again and we imagine a coil of wires, a helix. This is also sometimes referred to as a solenoid. So you'll hear me alternatively refer to a helix, a solenoid, or a coil. Here's what we do. We imagine the black lines are wires that are wrapped around some cylinder, and it's connected to a power supply. The current, of course, flows from the positive around to the negative and then back to the power supply. You see the current going up, 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 up the front, down the back, 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 like that. Okay, that's those dashed lines meant to show the wire behind where you can't see. That's where the current would be going down. And so here's what we do. We take our right hand, I'll draw this as RH, and this time the fingers go in the direction of the current. Remember, with right hand rule number 1, the fingers were the magnetic field. The thumb was the current. Now things are reversed. If your fingers are in the direction of current, then your thumb, see where I have room for this, there we go, your thumb will be pointing in the direction of the magnetic field, as we can see in this diagram and this. However, which end? The north end. So the thumb defines the magnetic field pointing to the north, which means the other end will be the south. Now, to see why this happens, again, think about this diagram that I explained to you and extend it into many, many loops down here, which you can see. See if you can figure out why one end is the north and one is the south. Remember, outside of a bar magnet, the lines go from north around to south. Everybody likes to go south for the winter. But that means on the inside of the magnet, they go from south to north and around. Now, there are a lot of neat applications of this thing called a helix or a coil or a solenoid. We're going to get to them next. First of all, I don't know if you've ever done this, but as a kid I did this a few times. It's kind of fun. Take, say, a 9-volt battery and a little bit of wire and an iron nail. Wrap the wire around the nail like so and connect opposite ends to opposite terminals of the 9-volt battery. Now I got to warn you, the battery is going to get hot as the current flows very rapidly because there's very little resistance in this circuit. Also, there is a chance that you will overheat the battery and damage it. I don't think a 9-volt battery would explode on you, but it could, or it could start leaking. So if you're going to do this, I recommend you wear eyewear, and you might even want to wear latex gloves for protection against any chemicals that may leak out. You certainly should keep an eye on how hot that battery is getting, and as it gets too hot, just disconnect these terminals and let the thing cool down. But the amazing thing is, you will now have yourself an electronic magnet, because you will be taking what we had back here, right, which behaves like a magnet, and you're doing something else. You are inserting some iron into the core of that helix. And what that does, since iron is what we call a ferromagnetic substance, the lining up of the atoms in the iron will actually intensify the magnetic field. And you'll have yourself a magnet. This nail will be able to pick up other nails or anything made of iron. It's kind of cool. In your textbook, grade 11s, there is a data table in section 14.2 which gives you the relative, what's called permeability, of different core substances such as iron, steel, which contains iron, and other alloys. And so you can use this to get an idea of what is the strength boost that I'm going to get if I use a solid core as opposed to just a hollow air core. Finally, a diagram here, you see a crane that is picking up pieces of metal, maybe working in a scrap metal yard. And what do we see right in here? This is actually an electromagnet. So this is a crane that uses an electric current wrapped around an iron core to pick up pieces of metal, and then when you turn off the current, you can put it back down. So it's kind of like an on-off magnet, as opposed to one of these, which is a permanent magnet that you can't turn on and off. Other things that are interesting about this setup here, the greater the number of turns that there are per centimeter or per meter, the more intense the magnetic field. So you can vary the strength of the magnetic field, and also the greater the current, the greater the magnetic field. And this means you can lift heavier and heavier things, or lighter and lighter things, or you could turn it off and drop things, which means, unlike permanent magnets where you're kind of stuck with what you had when it was manufactured, here you have a very versatile machine. Let's try a question from the grade 11 textbook. It says an electromagnet with 80 turns per centimeter and a current of 0.2 amps lifts 33 newtons of force, or exerts 33 newtons of force. So let's call this N1 for the number of turns per centimeter. 80 turns per centimeter. And the current 1, is 0.2 amps. The force that we get from this is 33 newtons. Now they tell you to calculate the force if the number of turns was increased, so we're going to go to N2 equal 120 turns per centimeter. However, they tell you that there's the number of turns per centimeter, here's the current, it's going to be only half of what it was, and so they ask you what will become of the force. Well, in your textbook you're going to learn a formula that says that the number of turns and the amount of current are directly proportional to the force. In other words, by taking 80 turns and increasing it to 120, we have multiplied by 1.5 the number of turns per centimeter. Well, that should take the 33 newtons of force and also multiply it by 1.5, which would give you something around 50 newtons. However, what have we done with the current here? We have divided it by 2, or if you want to think multiplication, that's multiplication by 1/2. So while the increase in the number of turns per centimeter gave us an increase of factor of 1.5, we also have to multiply by 1/2, so that in the end, what is our force going to be? We're going to take 33, multiply it by 1/2, and then we're also, times 1.5, and then we're also going to multiply it by 0.5, and when you round this off to 2 sig figs, I get 25 newtons. All right, and there's a formula in your book that shows that in a simple formula. All right, To move on, I have to close this, this presentation here, and I'm just going to open a new, don't want to save that, I'm going to open a new page because I ran out of actual space here. And so where are we? Desktop. Got to give me some room here so I can see where I'm at. Sorry folks, just bear with me. There we go. This is the one I'm looking for. Okay, so we continue now, and we're going to look at an interesting situation. What we've learned so far is that currents through a wire produce magnetic fields. And you can have a straight wire or you can have a coil. I want to go back to the straight wire here, and I'd like you to look at this setup. We have a battery with a positive terminal, wire connected, current flowing this way. It goes through a metal conductor like this, and of course it returns to the battery. Nothing too hard to understand there. The interesting thing is, I've placed this wire in between two ends of two different bar magnets. And so, if you remember, the magnetic field goes from north to south. Everyone likes to go south for the winter. So I've drawn in the magnetic field lines going to the right. Now, think about what's going on here. A current through a wire, according to right-hand rule number 1, it produces a magnetic field. The magnetic field due to the wire. However, there's also this magnetic field, which I've shown in magenta. This is another magnetic field. We could call it the external magnetic field. There are two different magnetic fields here. Now, what happens when you bring two magnets near one another, or two magnetic fields near one another? Well, they can attract or repel, according to the law of magnetic poles. In other words, they can exert force on one another. So there will be a force on this wire that is sitting in the magnetic field. The question is, what direction will the force be? Well, to figure it out, we have to learn what's called right-hand rule number 3. This is also known as the motor principle. You may also hear it described as the Lorentz force, or the formula for the Lorentz force. All of these are valid and apply. Here's what you do. You take your right hand, and your thumb is the current this time. So go over here, and with your right hand, place your thumb in the direction of current, which should be coming out of the page. All right? It's hard to draw three-dimensional shapes on a two-dimensional surface, but this is the current, which should be symbolized as out. Do you remember how to do that? It would be like an arrow coming out of the page toward your head, which would be a circle with a dot. Now, your fingers are supposed to point in the direction of magnetic field. So with your thumb still coming out of the page toward your eyes, orient your fingers of your right hand to the right in the direction of this magnetic field. Now, stop for a moment and ask yourself, what direction is the palm of your hand? If you did this correctly, the palm of your hand should be pointing up. And therefore, that is the direction of the force on this wire because its magnetic field and the external magnetic field are interacting. In other words, we've figured out a way to use electricity and magnetism to exert forces. And as you're going to see in a moment, we use this idea as the basis for an electric motor, which takes electric current and creates force to rotate something. For those of you who are really interested in exactly what's going on, check out this diagram down here. It shows a wire, this time with the current going into the page, and you see this curved gray arrow, which is due to right-hand rule number 1. This is the magnetic field due to the current in the wire. Now, this is a horseshoe magnet, as opposed to two ends of separate magnets like I have up here, and the magnetic field, of course, is north to south. So what do you notice? The magnetic field that's curved, right-hand rule number 1, that one is going up on this side, but the magnetic field due to the horseshoe magnet is going down. So we've got on this side two opposing magnetic fields. What happens when you have opposites? They attract. So the wire will feel an attraction to the left. On the other hand, on this side of the wire, the magnetic field due to the wire is down. It's going down due to right-hand rule number 1. And the horseshoe magnet field is pointing down as well. These are in the same direction. What happens with like magnetic fields? They repel. So the wire will be repelled from the right side, attracted to the left. It'll experience a force. If you use right-hand rule number 3, thumb is current, magnetic field is fingers, you will find that your palm is pointing to the left here. And so right-hand rule number 3 also works. Moving along. What is the application of this? Here's where things get a little interesting. I want you to consider another loop of current as shown in this diagram here. It's a single loop of wire in a sort of square loop, and both ends are connected to opposite terminals of the battery. Here's the negative, there's the positive. Follow the current. Up away from the positive, up this way, across, then down, and back to the negative terminal. In the meantime, there's a magnetic field, a south and a north, and so if we just use a different color here, and we remember everyone likes to go south for the winter, here's the external magnetic field. So here's what I want you to do. Over here, we have a current going up, that's the letter I. We have a magnetic field left, that's the letter B. There should be a force here. I want you to use right-hand rule number 3 to predict the direction of force here. You should find if you put your right fingers to the left, your right-hand fingers to the left, and your right-hand thumb up, the palm of your hand will be facing you. That means the force will be coming at you, a dot. That's the force. On the other side, the current is going down, like this. The magnetic field is still to the left, so take your right hand, fingers pointing to the left, thumb pointing down. This time, you're going to find that your palm points at the computer screen away from you. That's an X. Now, if we take this current loop and we allow it to pivot around some axis, it will start rotating. It'll rotate. If you could imagine yourself looking at this from up here, I'm going to draw your eye looking down on this. What would you find? You'd find this end going into the page, or the screen, this one coming out of the screen. That would be counterclockwise rotation as seen from this perspective. Of course, if you viewed it from below, you would see the opposite. You'd see clockwise rotation. Anyway, this would keep rotating until the negative side was over here and the positive side was over there. And then what would happen? Everything would reverse. The wire loop would go back. Well, therefore, this is kind of a strange situation where we have a loop of wire that keeps going back and forth on itself. However, hold that thought for 1 minute. Just pay attention to these springs here. What are these springs going to do? They'll hopefully prevent the wire from rotating too much. If it rotates too far, they'll kind of apply a force to pull it back. So here's what we're going to do with this idea. We're going to take those springs again. Here's the pivoting axis. Here's the loop, actually several loops of wire instead of just one, and we're going to wrap them around a core, a permeable core, to intensify the magnetic field. Now, stick a little arrow, like a needle or a pointer to this, and what have you got? You've got a device that rotates when you pass a current through it. And the more current, of course, the more force, the more it rotates. Of course, if you turn off the current, the springs make it rotate back to the original position. The needle, the pointer, can be set so that it points in a certain position depending on how much current there is. In other words, you've got a device where as you increase the current, the needle deflection also increases. You know what you've got? You've got the basis for an ammeter, like we've used in class, which have those needles that point to a certain position based on the amount of current, or the idea of a voltmeter, symbol is like this, which also works on a similar principle. Here's an amazing way we can translate electric current into a device that tells us how much electric current. So if you've ever wondered, How do these machines know how much current? This is it, because we got to know a little bit about forces and right-hand rule number 3. Let's carry this a step further. We're going to start talking about a motor now, and this is actually where we're going to finish off. But if you remember back here, I told you that this loop would rotate around halfway, and then the terminals would reverse themselves, and the forces would reverse, and it would go back. It would kind of flip back and forth all day. Well, if you could only do the following, if you could reverse the current after half of a rotation, you could keep the loop spinning in the same counterclockwise or clockwise direction. In other words, you would have the basis for a motor. And then you could do all sorts of stuff. You could use the motor to build a saw to cut wood. You could use it as the basis for wheels on a car that would get you from one place to another. You name it. How does it work? Here's that same loop, and I'm going to leave it to you to figure out the direction of the forces that are shown in red. They are here and there. Here's the positive terminal, there's the negative. Diagram A should be straightforward. To analyze it, just do the same thing we did over here, and you'll be able to figure it out. As the loop starts rotating, you see what happens. The force is still in the same direction, everything's cool. But once we get to here, we pass a point where in E, now the forces would normally reverse direction unless we could reverse the current. How do we reverse the current? Well, if you follow the terminals here, they don't change. So the battery doesn't move, or whatever's creating the current flow, that doesn't change. What does change all boils down to this diagram that I skipped a moment ago. It's called a split ring commutator. And if you look at it, what you can see is that the coil is attached to this, which is attached to the terminals of the battery. As it rotates around, it allows the wires to slip past the positive terminal and onto the negative terminal. And the negative terminal slips over to the positive terminal. And in doing so, we reverse the current flow through the wire in order to keep the loop spinning the same way. This is the basis of a direct current, a DC motor, where we don't need to reverse the current at the power source. We can just get it to change by reversing what terminals the wire loop is touching at different points in the cycle. And so we're going to finish up here with a few improvements on this DC motor. First of all, we don't need to use just one loop here. We could actually take an iron core, a permeable core, and wrap many sets of wires around it. These are called field windings, and by having many of these, we will not only have a stronger force, but at the rare moment, you'll notice if you study this carefully, every 180 degrees of rotation, if there's just one loop, every 180 degrees, we have to switch the current, and we have to switch the terminals we're touching, and therefore we lose current, we lose force, rotation slows a little bit. With many field windings like this, we can keep that force going. And the other thing we can do is we can use the electric current that we already have to wrap those around an iron core and intensify the magnetic field by creating essentially an electromagnet here. And this is the basis of modern DC motors. And so there you go. We've reached the end of the video. We've talked about a lot of stuff here. So let's just go over a few things. First of all, I didn't mention what's the fact of the video. So I'm going to do that now in reverse. Third fact of the video, which I think I forgot to type in here, is right-hand rule number 3. This is fact number 3. Learn how to use the right-hand rule number 3 so that if I give you a diagram, a scenario like this, you can figure out, given one of these two things, either field or force or current, given two of those, find the other one. All right? And the other one that the other two facts that I'd like you to know, let's see, I'm going to open the previous one, just go back, and where are we? Is this the one? I think this is the one I want. Just to go back, right-hand rule number 1 was a fact of the video, which I had written here. Okay, I just didn't mention it, so make sure you learn that. given the current, figure out the magnetic field, or given the magnetic field, figure out the current. Be able to do this in different orientations, like current going up or down, current going into the page or out of the page. And finally, the other right-hand rule number 2, make sure you learn that one, where we talked about how the thumb is the direction of north and the fingers are the direction of the current. So given one of those, figure out the other. Okay, and there you have it, folks. A review for the grade 12s, an introduction for the grade 11s. Thanks for watching, and I'll see you all in class. Take care.